In this question, we want to find the domain and range using the graph on the left. When I'm looking for domain and range from a graph, I like to use my ruler. And I like to hold my ruler or pencil vertically when I'm looking for domain, because if I hold it vertically, my ruler is running across the x scale. So I want to write it in interval notation, so I'm going to go from left to right. And the first time my ruler is hitting the graph is right here. It's a little bit hard to tell, but I believe this line is continuing on forever here. So I would say that this domain starts at -infinity and continues until we get to this vertical dashed line here. We're assuming that this line continues on forever as well. So once we get to this dashed line here, that vertical dashed line is an indication of a vertical asymptote. So it looks like this example has a vertical asymptote at x equals -3. So the vertical asymptote is an undefined spot on the graph, so the domain will start at -3. Then the graph continues right after that vertical asymptote. So the domain starts again at -3 and continues on to infinity. Now this is the domain written in interval notation, -infinity to -3, union with -3 to infinity. There's another way to write domain, and it's called set builder notation. And in set builder notation, we use curly braces. We state the name of the variable, in this case x, and then we draw this vertical line. That vertical line means such that, and what comes after the vertical line are the restrictions on that variable. So for this example, the only restriction is that x cannot equal -3. It can be any other real number besides -3. So then I'm looking for the range. I'm going to hold my ruler horizontally to find the range, because my ruler would be pointing to the y scale. As I go from bottom to top, the first time I hit the graph is right here at the x-axis, and that is a y value of 0. And I'm going to put a parenthesis on that because it looks as if the graph is getting closer and closer to the x-axis without ever reaching it. And that's an indication that this graph has a horizontal asymptote right on top of the x-axis. That's a horizontal asymptote at the line y equals 0. So my range is starting at 0 and continuing on to infinity. So this would be my range in interval notation, but if I wanted to use that other notation, set builder notation, I would use curly braces. And since I'm talking about the range, that would be the y. Y would be my variable. And I want to write the conditions or the restrictions on y. And in this example, the conditions are that y needs to be greater than 0. And so that would be your range in set builder notation, your domain in set builder notation above. On this question, we're given a graph of a function named g, which is this blue straight line, and another function called f, which is this red line. We have a couple questions over here, and the questions involve adding, subtracting, multiplying, and dividing these functions. And then because we have a number here, that's also involving evaluating these functions. So this notation, f plus g of -9, means that we want to do f of 9, g of 9, and then add the results together. I'm going to find f of 9 and g of 9 from the graph. So here is where x is equal to 9, and I'm going to go up to the graph to find out what the y value is at that point. And the y value at that point looks like it's 3. And that is for both the graph of f and the graph of g. So this one's going to be 3 plus 3 equals 6. Then I'll try the next one, f minus g of -9. So this time I want to go to an x value of -9, go up to the graph of, that's the graph of g, and record a y value of 1, and then up to the graph of f, which has a y value of 3. So for this example, f minus g of -9 is f of -9 minus g of -9. F of -9, that's the red graph, that has a y value of 3. And g of -9, that's the blue graph, that has a y value of 1. 3 minus 1 is 2. So f minus g of -9 is 2. So then I want to do the next one, which is g times g of 9. That's g of 9 times g of 9. And we've already found right here with an x value of 9, we have a y value of 3 for the graph of g. So we're going to do 3 times 3, which is 9. And then finally, f divided by g of 9 will be f of 9 divided by g of 9. And we've already found that for an x value of 9, we have a y value of 3 for both graphs. So this one will be 3 over 3, which is 1. So we found that f divided by g of 9 is equal to 1. For this question, we want to find the equation of any horizontal asymptotes of this rational function. So we're given this rational function here, f of x equals 8x squared minus 3x cubed over 7x cubed plus 4x squared minus x plus 4. Now when we're looking for horizontal asymptotes, the actual math behind finding horizontal asymptotes involves an operation called the limit that we learn about in calculus. So instead of us learning this operation that is for a later subject, what we have is a summary of different rules to handle different situations related to horizontal asymptotes, specifically for rational functions. So if we have our rational function being p of x over q of x, then it's going to be of this form here. This is a polynomial function in the numerator as well as a polynomial function in the denominator. And the rules are based on the degree of the numerator as well as the degree of the denominator. Now the degree of the numerator is the highest power on x and that's what we see here. It's listed as n. That's the degree of the numerator. It's the highest power on x from the numerator. And then it's also based on m, which is the highest power on x from the denominator. That's the degree of the denominator. And then what we do is we compare those values. If you have the degree of the numerator being smaller, if the two degrees are equal to each other, if the degree of the numerator is bigger by 1 and bigger by a lot, we have these different cases. So we need to determine the degree of the numerator and the degree of the denominator. So for our numerator, we can see that this term has a power of 2 on x, and this term has a power of 3 on x. The degree will be the higher of the two. So the degree of the numerator will be 3. And then looking at the denominator, this term has a power of 3 on x. This term has a power of 2 on x. This power is not listed, so we assume it to be 1. And this term, since it doesn't have a variable, has a degree of 0. So we're going to take the highest of those, which is 3, and that's the degree of the denominator. So since we have the degree of the numerator being 3 and the degree of the denominator being 3, that means that we're dealing with this second case of finding the horizontal asymptote. And in the second case, the line y equals a sub n over b sub n is the horizontal asymptote. Now a sub n and b sub m are the leading coefficients. These are the coefficients that are attached to those highest degree terms. So we want to use the coefficient of -3, which is attached to that highest term, that highest degree term of 3, and 7, which is attached to the highest degree term from the denominator. We call those the leading coefficients. So the horizontal asymptote is going to be the ratio of those two numbers. Our horizontal asymptote is y equals the ratio of -3, that's the leading coefficient from the numerator, with the leading coefficient from the denominator. So y equals -3/7 is the horizontal asymptote for this function. Thank you for checking out my videos. Have a great day.